Welcome to GriidAI. In this video, we will demonstrate how GriidAI can be used to perform a complete site suitability analysis for identifying the most suitable zones for sports centers in Riyadh. Selecting the right location for the sports facility is not just about finding open land. A good location must balance multiple spatial factors, such as where people live, where young and active populations are concentrated, how accessible the area is, how commercially active the surroundings are, whether there is already strong competition present, and where the land and terrain are physically suitable for development. To solve these, we use a grid based geospatial modeling approach. The study area is divided into 400-meter hexagonal grid cells, and each grid cell is evaluated using multiple indicators. Eventually, these indicators will be normalized and combined to perform a final suitability index ranging from 0 to 1, where higher value indicates stronger suitability. To continue, let's create a new session and rename it according to our objective. For this analysis, we will be using different types of geospatial and demographic datasets, each contributing to a specific part of the model. Let's upload the datasets one by one. Great, all the datasets have been uploaded. We can view these uploaded datasets into the data catalog. Let's check out the datasets that we are going to use. The first one is the Riyadh boundary. We can even visualize it on the map. As we can see, the boundary layer is a bounding box. This defines the area of interest and ensures that all the analysis that will be carry out will be restricted to the selected urban region. Next one is the hexagrid, which is the 400-meter hexagonal grid for the Riyadh. This grid acts as the base layer for the analysis. Each hexacell represents a small part of the city and contains a unique grid ID as well as the population value. This type of grid-based population is sourced from contour population dataset, which provides an H3 index-based population grids. For the demand modeling, we will be using an under 18 population raster sourced from the WorldPop dataset, which provides high resolution age-based population estimates. This will help us in identifying the areas where strong youth demand is present. We can even visualize this raster. We also use a demographic table containing different ages and gender percentage for the Riyadh. This type of data is sourced from statistical agencies such as the Saudi General Authority for Statistics. It helps us estimate physically active population and different types of family-oriented demand groups. Additionally, based upon the OpenStreetMaps, we are also using the building footprints and the road network for the region of interest. Apart from the already uploaded dataset, we will be also using the VIIRS nighttime data, ESA world cover land use land cover dataset, SRTM 30-meter DEM data, and different types of points of interest generated from OpenStreetMap. All these datasets we will be asking the agent to fetch from the web, and we will utilize them for our analysis in the later steps. Now let's start with our analysis. We will begin by checking the prepared Riyadh hexagrid. This grid is the base layer for the entire analysis, where each cell represents a small area of the city. GriidAI will verify the grid has the required information such as unique ID or the population value as well as the valid geometry. This ensures that the data is ready before we start actual calculating the suitability indicators. As you can see, the verification report has been generated by GriidAI, and it has also generated the statistics. Now let's proceed further. Now let's calculate the demand potential for each grid. This step helps identify where the strongest user base is located. We are going to consider the total population, under 18 population, physically active residents, and even family oriented demographic groups. Let's see what plan GriidAI has for execution. The basic intention here is to calculate the demand index based upon these different types of population parameters. So identify where high potential demand for sports and recreational facilities would be present. Let's give the permission to the agent for proceeding. Great, the analysis is completed and the demand index is generated. Let's check out the attribute table of our hexagrid to see if the new fields have been created. As you can see, these new fields are present and the final output, that is the demand index, has been calculated. Now let's move further to check out the commercial activity. This time we will be utilizing the nighttime lights data. We have asked the agent to fetch the VIIRS nighttime data from the web for our area of interest to proceed and generate the commercial potential. Here, areas with stronger nighttime brightness often indicate commercial zones, busy corridors, retail areas, and mixed use neighborhood. Let's grant the agent the permission to proceed by quickly validating the plan. Here, the agent processes the nighttime lights raster and summarizes the commercial intensity for each grid cell. This creates a commercial base layer that helps us identify economically active parts of the city. Great, the analysis is completed, and as you can see, a new raster based upon the commercial intensity from the nighttime data is also present. Let's check out the attribute table to see if the new columns for the commercial intensity have been generated. Yes, they are present. Now, to further analyze and increase the sensitivity of our commercial activity, we will also consider the access to different malls and shopping centers. So we have asked the agent to locate different types of malls based upon the points of interest from the OpenStreetMap and generate 5, 10 and 15-meter driving catchments from each grid. Areas closer to these malls will receive higher scores, and they are likely to benefit from stronger commercial activity and better urban services. The small accessibility score is then eventually combined with the nighttime light score to create the final commercial index. Great, the process is completed. Let's check out the hexagrid to see if the isochrones generated have updated the commercial index. As we can see, the mol POIs have also been generated and used to generate the commercial index. Let's move forward. Now let's measure the accessibility. We have asked the agent to identify important public services such as schools, universities, bus stops and train stations, and then create another 5, 10 and 15-meter walking catchments around these locations. Grid cells that will fall within these distances will receive higher scores. This would help in highlighting areas that are better connected to education facilities and public transport, making them convenient for our users. Let's briefly validate the plan and grant the agent the permission to proceed. Great, the analysis is completed and as per the agent, the accessibility index has been generated. Let's check out the attribute table to see the results. As we can see, the new columns for the accessibility have been added. Now let's proceed further and identify the competition. We have asked the agent to generate POIs for the fitness centers, gyms or sports halls, etc. These locations will represent the competing services in the area. Using the driving catchments again, the agent will be measuring many competitors that will influence the grid. Areas with more nearby competition receive a higher competition score, which will be later treated as a negative factor in the final suitability model. Great, the result is completed. Let's check out the hexagrid. Once again, the attribute table to see if the new columns are there. As you can see, the competition index has been created. Now, let's move ahead and check whether the land is suitable for development. This step considers the building density, terrain as well as land cover. So we have asked the agent to fetch land use, land cover and terrain data from the web. Areas that are highly built up may have less available space, and flat terrain is generally more suitable than steep terrain for the construction. Open land, bare land, shrubland, and grassland are more suitable than water bodies or dense built up areas. So, these are some of the factors combined into a land and terrain readiness index, showing us which areas are physically more practical for future development. The agent has also come up with a plan. Let's check it out briefly before granting the agent the permission for proceeding. Great. The Land and Terrain Index LRI has been generated. As you can see, the two new rasters for DEM as well as LULC have been rightly fetched from the web and clipped to our study area. We can even visualize them. Now, let's check out the attribute table of the grid to see whether the new index has been computed correctly. Great. As you can see, the LRI index has been generated. Now, let's move ahead. After all, the individual indices we have computed. Now let's ask the agent to combine them to generate the final suitability index. We will ask the agent to prepare a model which will give importance to demand, accessibility, commercial activity as well as land readiness while reducing the score in areas where high competition is present. Each grid cell will receive a final score between 0 and 1. The scores are then classified into four categories very high, high, moderate, and low suitability. This gives us a clear map of where sports and recreation centers are most likely to succeed. Great. The final suitability index has been calculated and added to the hexagrid as per the agent. Let's visualize it quickly. As you can see, this FSI stands for the final suitability index has been computed both in its normalized and raw forms, and later on even classified version is present. We can even check out the statistics computed by agent, where the agent has counted the grids in each of the classes of high, very high, moderate and low. Now we have reached the conclusion of the case study. Before that, for visualization, we will ask the agent to generate the maps from the results and draw further insights. We will create the final map of the suitability index. We have also asked the agent to identify the top 10 suitable grid cells and group by high scoring cells into a practical development clusters. Let's briefly check out the plan the agent is laid out proceeding, and let's grant it the permission. Finally, the agent will also explain why certain areas perform better, whether due to stronger demand, better accessibility, higher commercial activity, better land readiness, or lower competition, and some of them look poor for the suitability of the sports centers. This turns the model output into decision ready information that can support planning and site selection instantly. Great, the results have been generated and the statistics have also been calculated. Let's check out the top 10% suitability hexagrid cells. As you can see, these are some of the most suitable grids where a sports center can be successfully run. Let's check out the final summary provided by the agent. Overall suitability pattern is spatially clustered rather than uniform, with a clear top 10% forming multiple contiguous patches plus some smaller isolated pockets. It has also provided us with the latitude and longitude with additional strong clusters with different latitude and longitude to identify the exact locations. The primary drivers for high suitability are mainly the accessibility index, the demographic demand, and the commercial activity. Where there is high competition, it has reduced the suitability significantly. And we have also identified the most suitable clusters or zones where the sports centers can be taken up immediately. This complete workflow demonstrates how site selection can be transformed from a manual subjective process into a transparent data driven spatial modeling. By combining population, demographic, nighttime lights, points of interest, road network travel times, competition analysis, building density, elevation, slope, aspect, land cover, the grid AI produces a comprehensive suitability score for every 400-meter grid cell. This strength of approach is explainability. Every final score can be traced back to its individual components, allowing planners and decision makers to understand not only where suitable sites are located but why they are suitable. Instead of switching between multiple GIS tools, writing separate scripts, downloading data manually, and performing repeated spatial joins, the entire process is executed inside GriidAI through structured prompts. This makes the workflow faster, more repeatable, and easily validate. It also allows the methodology to be adjusted for other cities, other areas of interest, other facility types, or different planning priorities. The final result is an end-to-end AI-assisted geospatial decision support workflow for identifying the most promising locations for future sports and recreational infrastructure. With GriidAI, complex site suitability modeling becomes a guided, explainable, and repeated workflow, from raw geospatial data to final decision-ready maps and insights.